A two-sun Earth sounds like pure science fiction. We imagine beautiful, eternal golden hours on alien worlds. But in reality, a binary star system is a chaotic dance. Two stars orbit a shared center of mass, constantly pulling at the space around them. For Earth, a second sun wouldn't be a paradise. It would likely turn our stable Goldilocks environment into a volatile, dangerous world. Our stability relies on a singular, predictable relationship with our sun. Adding a second star introduces forces that life as we know it simply couldn't handle. In binary star systems, planets exist in two primary configurations. First is the S-type orbit, where a planet orbits only one of the two stars. Because the second star acts as a constant gravitational disruptor, S-type orbits are often unstable. Over time, the planet may be ejected from the system or collide with a star. The alternative is the P-type, or circumbinary orbit. Here, the planet circles both stars as they dance around a common center of gravity. P-type configurations are generally more stable, offering a consistent environment compared to the volatile dynamics of S-type systems. In our solar system, the habitable zone is a stable, consistent region where liquid water can exist. It is a predictable band defined by our single sun's steady output. In a binary system, this zone flickers chaotically. As two stars orbit each other, the radiation flux reaching the planet shifts dramatically, creating intense seasonal swings. The resulting radiation spectrum is unpredictable. This high-energy flux would create environmental conditions that exceed the biological survival limits for complex Earth-based life. This flickering habitable zone is one of the greatest obstacles to habitability in two-sun systems. If one of the stars in a binary system is a red dwarf, the planetary environment becomes lethal. These stars emit intense X-ray and UV radiation. Earth's ozone layer acts as a crucial shield. However, constant bombardment from a nearby companion star would deplete this shield, leaving the surface exposed. Without the ozone layer, lethal radiation reaches the surface, causing DNA damage and destroying the foundations for complex life. Ultimately, atmospheric stripping renders a planet uninhabitable, regardless of whether the temperatures are theoretically stable. In a binary system, gravitational tides from a second star can fundamentally alter planetary rotation. This often leads to tidal locking, where the planet's rotation matches its orbit, keeping one side permanently facing the star. The result is a geologically and climatically volatile world. One hemisphere is trapped in a permanent, scorching noon, while the other remains a frozen, dark wasteland. This eliminates the 24-hour day-night cycle essential for life as we know it. Essentially, the constant gravitational tugging from a second star disrupts the planet's equilibrium, turning a habitable world into a hostile, binary locked environment. Kepler-16b is our primary benchmark for planets orbiting two stars. Often compared to the fictional world Tatooine, data reveals it is actually a cold, massive gas giant, not a terrestrial paradise. Current data suggests terrestrial, Earth-like planets rarely survive the violent gravitational landscape of early binary formation. The orbital noise tends to eject smaller rocky worlds or lead to collision. The lesson from Kepler-16b is clear. Circumbinary systems are inherently hostile to small, rocky worlds. Finding an Earth-like planet in such a volatile environment remains the ultimate challenge in exoplanetary science. Our solar system is defined by a rare, elegant stability. Earth thrives because it orbits a single, consistent star in a near-circular path. This stable orbit allows for predictable Milankovitch cycles. These slow changes in Earth's tilt and orbit act as the heartbeat of our long-term climate stability. However, adding a second star introduces gravitational noise. This two-sun scenario creates chaotic forces that would tear apart our delicate orbital clockwork. Without this solitary stability, the stable conditions required for complex life and the rise of human civilization simply would not exist. We live in a Goldilocks system. While a two-sun world is a compelling aesthetic dream, the reality of such a system is far from a scenic paradise. Physics dictates that such worlds face chaotic gravitational tides, extreme climate shifts, and intense stripping radiation from binary partners. These environments would likely be geologically volatile, scarred by constant tidal heating and seismic activity. Statistically, Stable binary systems capable of supporting life are incredibly rare. Our solitary sun provides the unique stability that allowed our biosphere to flourish.